Okay, now we are going to develop statistical criteria or how to analyze estimators and how to argue that an estimator is good but others are bad. So to do that, you have to first understand the fact that an estimator is random. We discussed that in the previous chapter. So remember, the random sampling and sampling distribution is like this. There is an infinite number of like infinite size, like so the population, which contains infinite number of objects. There is a population, and you are taking simply suppose that 1,000 observations from the population, 1,000 samples from the population, and from based on those 1,000 observations, you calculate an estimator. That is like it can be sample average or sample median. Like I gave you some examples. Whatever you can calculate those observations can be an estimator. So you calculate just one number from 1,000 observations. And then in the previous chapter, we understood those 1,000 random sampling, like random sampling of 1,000 samples as one experiment. So from this one experiment, you have one estimator as a result. One experiment of one random sampling results in one estimator. And if you repeat random sampling, your value of the estimator will change because those 1,000 numbers will be different, right? So in that sense, the estimator is random, and the distribution of the estimator is a sampling distribution, right? So the randomness is coming from the random sampling. The underlying experiment is random sampling of size n, right? And then first, we are going to think about those distribution of estimator. Estimator, I said, is random. So you can think about its probability distribution. Ideally, what you want here is a perfect estimator would satisfy this. Your estimator theta hat for parameter theta equals like always true. So the estimator equals to the true parameter theta and that probability is 1. So theta hat is random and theta is not random. The true theta is not random, but they are the same all the time. This is a perfect estimator, and of course it is impossible. In reality, there won't be any estimator like this at all. If there is, then it means you know the answer. The only case that this is possible is when the parameter is known. Otherwise, it cannot be true. But what I want to say here is you have to think about randomness in the estimator. That's the starting point to analyze the good estimator. What is a good estimator? So first, in most cases, we learned the sampling distribution converges approximately to a normal distribution. So think about a normal distribution. And the normal distribution could be centered around the true parameter. Say, true parameter is here, and your estimator is distributed around the true parameter, which is good. You want your estimator to be centered around the true parameter, or the expectation of your estimator is the true parameter. But based on this distribution, your estimator could be like somewhere outside, different from the true parameter. The true value of the parameter is at the center, but your realization of the estimator could be here, for example. Then this much is the estimation error. Estimation error also follows the same distribution, right? If your like the if your realization is here, estimation is this much, error is this much, and then probability is this much. So estimation error is also random. It is just a transformation of your estimator by taking the difference between estimator and the true parameter, right? This is what we are interested in. We'd like to study estimation error. This is the basis of our criteria. Then, for example, you can think about this way. The probability on the other side, on the right-hand side, is overestimation probability. So your estimator is larger than the true parameter, overestimation, right? And of course, then the other side is underestimation probability. If your estimator is somewhere here, that means your estimator is smaller than the true parameter. So, and in this example, if the sampling distribution of the estimator is normal, and the center of that sampling distribution is the true parameter, then overestimation probability and underestimation probability are equal. There is no over or underestimation on average, right? And or you may think, I'm just giving you some examples how to think about this probability. Or you can think about this certain radius. If you allow certain radius, for example, I want to have an estimator whose error is smaller than plus minus 1, for example. And then, based on the sampling distribution, you can calculate the probability within plus minus 1 around the true parameter. So true parameter is here, plus 1, say, and minus 1 here, and then you know the probability around it. So if the distribution was more concentrated around the true parameter, this probability will be greater, which is good. So these are just examples of criteria we could think of when we define what is a good estimator, right? So then also let's think about this. So far I explained as if the mean of the sampling distribution is always the true parameter. Actually, not necessarily. So the true parameter is here, but the estimator's sampling distribution could be misaligned. So say orange. Orange is a new estimator. The orange estimator has larger probability of overestimation. It's overestimating the true parameter. More likely to overestimate. So this is first thing you have to think about, whether it is like overestimating or underestimating. On average, you want exactly you want those two, overestimation and underestimation, cancel out each other on average. That's what you want. We are going to formulate that as criterion number 1. And second, if you compare green estimator and blue estimator, then both of them are correctly centered around the true parameter. So for both of them, on average, they are correct. On average, there is no overestimation nor underestimation because they cancel out. Those probabilities cancel out. But the difference is the variability. Green estimator has larger variance, which implies, like for example, the probability of having this much small estimator is pretty unlikely for the blue estimator, but green estimator has quite a bit of probability below this level. So when the probability distribution, sampling distribution is more variable, that means that estimator is less reliable or has, on average, larger estimation errors, like deviates more from the true parameter, right? Exactly, that's the idea of variance. So we want the estimator to have more probability closer to the true parameter, right? So if you compare these two, the blue estimator is better than the green, right? So, okay, we learned two things. Assuming that the sampling distribution is normal, first, we'd like to check where the center is first. And second, we would like to check how big the spread is, the variability is. So those are related to mean and variance. So our criteria will be based on the mean and the variance of the sampling distribution for the estimator. Okay, so this is the formulation. We are going to discuss these two criteria to evaluate estimators. We will check estimators, and if they satisfy these two conditions, they are good estimators. First condition is that the expected value of the estimator must equal to the true parameter. So on average, expectedly, your estimator must be correct. Sometimes it underestimates, sometimes it overestimates, but on average, they cancel out and must be unbiased. Second, the variance of the estimator must be small. Of course, the smaller the better. If it could be 0, that would be perfect, but it's unrealistic. Zero variance is unrealistic. It's usually not possible. So when you need a kind of comparison, you need to compare two estimators, and then the smaller is the better, right? By the way, in mathematical statistics, there are many more criteria than this. I'm just giving you two simple criteria as an introduction to this theory. It's a theory for estimation. So textbooks may have more like criteria like consistency or like asymptotic unbiasedness, something like that. But I will discuss only two of them. That's enough, I guess, in here. Uh, then, so what you need to learn from here is that the criteria are basically based on sampling distribution. So the mean and the variance of the estimator is from the sampling distribution of the estimator, and also based on the actual value of the true parameter. So that is a challenge. So you don't observe the true parameter, right? Even if you know the mean of the estimator, you don't know if that's correct or not. That is number one problem. And number two, how do you estimate the expected value of the estimator? You estimate only once. You cannot repeat that. So random sampling realizes only once. You never repeat a random sampling in practice. So how can we argue this? That is possible in theory. So theoretically, we can show that a parameter on estimator has the expectation that equals the true parameter, or an estimator has smaller variance than another. So it is a purely theoretical discussion, and we will still it's not a big problem, and in most cases it's not a big problem. The first criterion is called unbiasedness. So biased, so if it is not satisfied, then you say an estimator is biased. That means this can be understood this way. Theta hat the estimator minus the true parameter. If you knew the true parameter, then you must be able to calculate that. And then this is the estimation error. And as I said, it is random. And if it's positive, overestimation. If negative, underestimation. What we want here is this can happen. It may be negative or positive. That can happen. But what I want is their expected value must be 0. So the expected estimation error is called the bias. And what I want here is the bias to be 0. I want the bias to be 0. And then we say the estimator is unbiased, right? On average, it's neither overestimating nor underestimating. If the bias is positive, that means on average, overestimation is likely. And vice versa. If the bias is negative, that means usually underestimates. Right? So it's the bias is about the mean. So if you just simply think it as the mean equal to the true parameter, then it is easier to understand. So then now we can use this term to compare these two estimators. Exactly using the same intuition as before, the orange estimator has higher probability greater than the true parameter. More probability of overestimation than the underestimation. So it is biased, positively biased. So we can conclude that the blue estimator is better. All right, this is usually the unbiasedness is usually considered as the number one criterion. So if you can choose only one criterion, unbiasedness is that. So if an estimator is biased, then without considering its variance, it's kind of disqualified. Usually. Okay, then second criterion is about the variance, which is called efficiency. So variance or standard deviation. Standard deviation of an estimator has a special name called standard error. So you can think it as standard deviation of estimation error. This is simply standard error, right? So then, as I said, smaller standard error means the estimators are more reliable, right? So that means suppose consider it this way. If you can repeat the random sampling, then suppose you observe 1,000 observations in the first repetition and calculate an estimator. And then repeat the random sampling, and in another set of 1,000 observations, you calculate the same estimator again and got another value. What you want here is you want these two estimators be similar so that your estimation process is more reliable. If they are very different, that means something is not going well. They are estimating the same parameter, but the answers are different in two different experiments. So you want them to be close to each other, which means the standard deviation is small. So smaller standard deviation is called efficiency, right? So we say if theta 1 hat, the first estimator has a standard deviation smaller than that of the second estimator, then we say the first estimator is more efficient than the second one. Then, why do you think it's called efficiency? So why do we call it efficiency, not just reliability or small standard error? Like there could be more intuitive names, but it's called efficiency. Then before talking about that, so this is an example. So if you compare blue and green, then you can say that more formally, statistically say that the blue is more efficient than green. In other words, like intuition is same. Blue is more reliable, more closer to the true parameter, so it's a better. Then why do we say it is efficient? Why the name is efficiency? Then the idea is, I would say this way. The standard error is usually determined by this form. You remember? In the previous chapter, the standard deviation of the sample average is the standard deviation of the single observation divided by the square root of sample size. So in many cases, not only the sample average, but in most cases in statistics, the standard deviation is closely related to the sample size. So sample size is one of the main factors that determine the standard error. So that means what you need to do here is, if you have certain observations, you have to efficiently use them to minimize the standard error. You have to use all of them. If you don't use some of them, then you are losing efficiency, because the effective sample size would be smaller. So if the sample size is the same, then you have to use it more efficiently. And of course, you have to fully utilize the sample size. So in that sense, it's called efficiency. How efficiently you extract information from the same size of sample. It's just my guess. By the way, I don't know who first named it efficiency, but it's my guess why it's named efficiency. Okay, then for example, if you compare the mean and the median, even if they are estimating the same parameter, still we can say the mean is better, because the mean has smaller standard deviation. Approximately, like sample mean and sample median standard deviation is approximately 1.25 times larger than that of the sample mean. So sample mean is using the sample more efficiently. So it's more efficient. Like, this is a simple summary of these two criteria. So if you imagine statistical inference is like shooting at a target, and then unbiasedness is like it's about the center of the results. Like it's like 0 point is correctly at the bullseye. So aiming at here and aiming at here, that is correct. So that's about bias. And so in this case, the 0 point aiming at here and aiming at here. So already the 0 point is away from the bullseye. So in that sense, these are biased. And second criteria is efficiency. It's about how reliable, how much it changes over and over, like different shots. So in here, you are targeting here, and most of the shots are correctly going to the target. But in the second, in here bottom image, even if you are correctly aiming at the bullseye, the results are going like moving away from the target 0 point. So it's not efficient. So even if you aimed at the correct point, still the result could be unreliable. It's going away. And then in this case, even if the aim point is away from the bullseye, which is not good, but still it's like they are reliable, like getting together. They're close to each other. So if you could just readjust the target to the bullseye, then your estimator could be better. So in the end, this one is the best estimator, both efficient and unbiased. And this is of course the worst, unreliable and biased. Okay, this is a simple summary of two criteria to define a good estimator. Okay, the video gets too long, so I will stop here and we'll wrap up the simple estimation theory in the next video. Thank you for watching.